Okay, now let's move forward a little bit and let's define max n. And max n gives me the maximum of a list. So what I have, for example, is max n of, and here's the syntax for a list. I'm using a square bracket, 1, 3, 5, 7, 2, right? And the max of that should be equal to 7, which is just the maximum element in a list. Okay. Now, notation-wise, excess sub 0 will be the first element, right? So excess is that, right? Then excess sub 0 is equal to 1. This is the first element in the list. And this is Python, okay? Excess 1 colon, right? What this means is the rest of the list. Or I should say the list starting at element 1, which will be equal to 3, 5, 7, and 2. Okay, this is very typical of how we work with lists. We do something with the first element, and then we do something with the rest of the list. Okay, which is actually a list. So let's see. When we start up, we say the maximum value is just the first element. What if there is no first element? What if it is empty? We'll think about that later, right? This function will simply crash in that case, right? But for actual lists that are not empty, then the element we start out by saying is the first element, and then we hop in a loop that considers each of the remaining elements, right? And if any of those is greater than the maximum so far, then we change the maximum so far to be that element. Okay, this is kind of the propagating maximum. Okay. Now, I expect you all to be able to read this code and go, yeah, that's exactly what he does. That's because you've been brainwashed into this style of programming, right? Where we do something and we hop a loop that keeps updating a variable. It's a great style of programming. It's called imperative programming. But if you have never taken programming before and I showed you this, you'd be like, what? Okay, that doesn't make any sense. And whereas some of the previous one, like if x is greater than y, then return x, otherwise return y, you would have thought, yeah, that makes sense. Okay, so these loops are a little complicated. They make things more difficult. Now, let's do the same thing with logic, okay? And I have to introduce this kind of notation here. So again, I'm going to say that x is equal to 1, 2, I should have called it x's, 5, 7, okay? Then the way that we write this is we say that x is equal to x followed by r, okay? And if this is the case, right, then x is actually equal to 1. That's how we get the first element. This is a vertical bar, right? And this gives me the first element. And this is everything else, which means that it's a list. Okay? So r is actually equal to the list 2, 5, 7. All right? Notice, for example, that if x's is equal to the list just containing 1, right, then if I say that x's is equal to x followed by r, then x is 1 still because it's the first element, but now r is going to be the empty list. Okay, so that's what this notation here is, right? X followed by x's, right? So let's see what we have. If max n, if I'm talking about a list that has just one element, then that element is the maximum. Makes sense, right? If I'm looking at a list that has x followed by x's, right? Then I want to find out what the maximum of x's is. And if that maximum is greater than x, then guess what? X is the maximum of the entire list, right? So for example, if I have something like 7, 3, 1, right? Then, and let's say that that's equal to x followed by x's, right? Then x is 7, x's is 3, 1. So the maximum of x's is 3. Makes sense. 7 is bigger than 3, so the maximum of my list is actually 7. And again, if you look at that list, yeah, that seems to be true. Now here is the other case when x is not greater than max n of x's. Well, in that case, right, the max n of x and x's is just simply the maximum of the rest. This is the case where x-axis is equal to, for example, 3, 7, 5, right? So that 3 is not bigger than the maximum of x's, which is 7. All right. I want you to kind of compare and contrast this definition down here where we're using the ACL2 or the Lisp notation. Okay. So a few things that I want to point out. First thing is I only want you to look at this part right here for now. Okay? All right, so I have three cases, number 1, number 2, and number 3. To do that, I'm going to need two conditions. And here they are. So this is case number 1. Okay? This is case number 3. And this one here is case number 2. Right? So let's see how we got those. In ACL2, we don't actually use the vertical bar notation. We don't use that in ACL2 or in Lisp. Okay. Instead, we have two kind of special functions. The first one is first. First of, let's say the list 1, 2, 3 is equal to 1, right? So basically, it's the x in x followed by x's. Okay. And rest of 1, 2, 3 is equal to the list 2, 3. Okay. So it is like x's in x followed by x's. Okay, so we'll use those two functions to kind of to split up a list. Okay. Now the other thing that we need to know is const p. Oops, const p of something, right? And this returns true. Well, let me tell you when it returns false. It returns false if the something is equal to the empty list. And it returns true otherwise. Okay? Or I guess I should say if it's a pair. Okay? So, const p of rest x. Okay? So, rest x's rather. So I take x's. Let's say x's is equal to 1, 2, 3. Okay? So rest x's is going to be equal to 2, 3, right? Because it's everything except the first element. And now I ask, const p, is that equal to the empty list? Okay, and the answer, of course, is false, right? If the answer is true, then what does that tell me? It tells me that I have a list that has only one element, because when I take that element away, I get the empty list, right? That is precisely this case here, number 1, right? So, if const p is false, then I go to the number 1 case where I simply return the first element of x's. That's how we translated this logic into ACL2. Okay, so now I know that I'm in a situation where I don't have a list containing only one element, right? So I mean one of these two. How do I know? Well, I'm going to need to test this condition. So is the first element of x's, that is just first x's, is that greater than the maximum of the remaining, right? If that's true, then I am in case 2. So the answer is just the first element. If it's false, then I'm in case 3. And notice that in case 3, then it's the maximum of that, right? So you see that these two notations, even though they look very, very different, are actually defining the same function, okay? There's just one detail that I brought up earlier, and now I'm going to cover it. What if I actually call it with x's equals the empty list? I can't take the first x's. I can't take the rest x's, right? So I got to do something. So what I'll do is first I'll check, right? And if you sent me an empty list, which means that const p of xs is false. Remember, const p, it returns true when I actually have a list that I'm working with that's not empty. Okay, so if that is false, then we're going to return nil, right? This is kind of like an error case. Okay, and I'm going to call it case 0, which I actually don't have here, right? But you know, when we're writing axioms, it's okay not to include the errors because maybe it's just not defined in that case. I can't tell you what the maximum of an empty list is in the logic sense. But in the case when I'm writing a function, I actually need to check for those cases. So in programming, I do want to know. So that's why I checked. Okay. All right. Let's look at some other notation for functions. Okay. And you'll notice that I actually went ahead and added the empty case, right? So max of an empty case is none. This is a special constant, right? Which means error, okay? Right? None is it's common in many systems. Think of it as the null pointer, right? And this is actually a different way to find the maximum of a list. Okay, so the way that we did it before, if it's a list that contains only one element, then there's my maximum. It's that element, right? Otherwise, what I do is I take the first element and I find the maximum of the rest and then pick whichever one's bigger. Makes sense. What this definition does is it says, oh, is it a list that contains just one element? Okay, then that's it, right? Is it a list that contains two or more elements? Then let's just look at the first two elements. Replace those first two elements with the maximum of those two elements, and then find the maximum of that list that has the maximum of those elements and the rest. Okay, so that's actually the idiom that's used in this particular language, and this particular language is Scala. Okay, and you may have heard of it because Scala compiles into the JVM, and Scala is functional. It's a functional language, unlike Java. And if you're thinking, so what, right? Actually, we like functional languages for things like parallelism, for things like running inside a GPU or running across multiple servers and so on. So it's actually a big deal. We have a functional language that compiles to the JVM. People like that. Okay. And anyway, here's the actual definition. What we're saying is, what exactly is access, right? So I say that access is a list of integer. So pattern match it, right? If it's actually nil, then the answer is none. That's this, right? If the thing is a list of an element, just one integer, then just return that, right? That's actually the answer. Otherwise, it looks like this is the first element, this is the second element, and this is the rest of the elements, right? And so what we'll do is we'll construct a new list that has the same rest, okay? But here we have the maximum, and I'm going to say the maximum too of the first and second elements, right? And you can see that this also computes maximum of an entire list, right? Again, the point is not to learn Scala, right? That's not what I'm trying to get you to do. The point is just to help you recognize where functions exist.